Have you ever wondered what everything is actually made of? I mean, really made of? Well, today we're going to crack the code of matter itself. We're going on a journey from ancient philosophy all the way to modern chemistry to find out what the fundamental building blocks of our universe really are. So let's start right there with that huge question that people have been asking for thousands of years. What is the world really made of? And you know what? We're going to treat this like a detective story. We're going to follow the clues that led scientists to one of the most incredible discoveries ever. And our story, well, it doesn't start in some high-tech lab with a bunch of fancy equipment. Nope. It starts thousands of years ago, inside the minds of some brilliant ancient philosophers. This is absolutely fascinating. Around 500 BC, you had an Indian philosopher, Maharishi Kanad, who came up with this idea that if you just keep dividing matter, you'll eventually hit a point where you can't divide it anymore. He called this tiny particle paramanu. Now get this, at the exact same time, halfway across the world in Greece, a guy named Democritus had the exact same idea. He called his version atomus, which means indivisible. Two totally different cultures, one profound idea. Everything must be made of some fundamental, unbreakable little piece. So for centuries, this was all just a cool philosophical idea to debate. But then, in the 18th century, things started to change. Scientists like the great Antoine Lavoisier started finding the first real clues in our mystery. And they discovered that matter, well, it plays by a very strict set of rules. The first huge rule they figured out was the law of conservation of mass. And its beauty is just how simple it is. It basically says that in any chemical reaction, you can't just poof, create matter out of thin air, and you can't make it disappear either. So the total weight of what you start with has to be exactly the same as the total weight of what you end with. Nothing just vanishes. Okay, so look at this reaction right here. It shows this perfectly. We're starting with 5.3 grams of sodium carbonate and 6 grams of ethanoic acid. Add those up, and you get a total starting mass of 11.3 grams. Now, after the reaction happens, we get 3 totally new substances. So let's add up their masses. What do you think we're going to get? You got it, exactly 11.3 grams. The mass is perfectly conserved. It's all still there. It's just been rearranged into new things. This was clue number 1. A truly groundbreaking discovery that proved matter isn't magic. It follows predictable laws. All right, on to our second major clue, which was discovered by Joseph Proust. It's called the law of constant proportions. And the easiest way to think about this is that pure chemical compounds are like recipes. Take water, for example. It always has the same recipe, a fixed ratio of hydrogen and oxygen by mass. It doesn't matter if you get that water from an iceberg or a river or you make it in a lab, the recipe is always the same. So let's put this to a quick test. We know the mass ratio for water is 1 part hydrogen to 8 parts oxygen. So if you've got 3 grams of hydrogen, how many grams of oxygen would you need to follow that recipe and make water? Yep, you'd need exactly 24 grams. This whole fixed recipe rule was the second giant piece of our puzzle. So we've got these 2 huge clues on the table, right? Mass is always conserved, and compounds have fixed recipes. The stage was now set for our master detective, a guy named John Dalton, to step in and finally crack the case. He's the one who connected all the clues into one single, powerful theory. And Dalton's central idea was a total game changer. He basically took that ancient Greek idea of atomos and gave it a real scientific backbone. He proposed that, yes, all matter is made of these tiny particles called atoms, and these are the very things that are getting rearranged during chemical reactions. And here's the really brilliant part. His theory perfectly explained the clues that everyone had been finding. The reason mass is conserved? Well, it's because reactions are just rearranging atoms, not creating or destroying them. And the reason compounds have fixed recipes? Because atoms combine in simple, fixed, whole number ratios. It all just clicked into place. Dalton had cracked the case. Okay, so now that we have Dalton's theory as our guide, let's properly define these fundamental building blocks of matter. What exactly is an atom, and how is it different from a molecule? First up, the atom. You can think of it like the smallest possible Lego brick of a particular element. It's the absolute smallest piece you can have that is still, say, gold or carbon or oxygen. It's the fundamental building block of everything. So what happens when those Lego bricks, those atoms, start snapping together? Well, you get a molecule. A molecule is simply a team of 2 or more atoms that are bonded together, and it's a stable little unit that can exist all on its own.
Okay, so let's break that down one more time. An atom is the basic unit of an element. A molecule is what you get when those atoms team up. So, for example, a single oxygen atom is just O, but the oxygen that we all breathe, that's actually the molecule O2, a little team of two oxygen atoms bonded together.
And this brings us to a cool word, atomicity. It's just a fancy way of saying how many atoms are in that molecule's team. Some elements, like helium, are perfectly happy to fly solo. We call them monoatomic. Others, like the oxygen we breathe, form pairs, so they're diatomic. And then you get some really big teams, like sulfur, which can form a ring of 8 atoms. Just one last key particle you should know about is the ion. An ion is simply an atom that has either gained or lost an electron, which gives it an electrical charge. So for instance, regular table salt is really just a big cluster of positively charged sodium ions and negatively charged chlorine ions, all stuck together. So at this point, scientists had a pretty good handle on this invisible world of atoms. But the next step was huge. They had to create a language to actually describe it all, a kind of secret code for chemistry. Dalton himself actually started with these little pictorial symbols, but they were kind of clunky, you know? Then a chemist named Berzelius came along and had a much better idea. He said, hey, why don't we just use 1 or 2 letters from the element's name? That system was so much better that it stuck, and today it's all standardized by an international group called the IUPAC. It's why sodium is Na, from its Latin name, natrium. And using these symbols lets us create what we call a chemical formula. This is the secret code in action. It's an incredibly powerful shorthand that can tell a chemist everything they need to know about what a compound is made of, all in just a few letters and numbers. Just look at this table to see how it works. We all know what water is, right? But its secret code is H2O. That little 2 is key. It tells us there are 2 hydrogen atoms for every 1 oxygen atom. It's a simple, elegant, universal language for describing all the stuff around us. And this code, it does more than just name things. It actually lets us calculate a molecule's mass. It's so cool. We know a hydrogen atom has a mass of about 1 unit, and oxygen is about 16. So for H2O, you just do the math. 2 hydrogens, that's 2, plus 1 oxygen, that's 16, which gives you a total molecular mass of 18. It's incredibly elegant. So let's end with a final thought to chew on. We've learned today that all atoms are ancient, and they're never created or destroyed. They only ever get rearranged. If that's true, what does it really mean when you throw something away? Those atoms don't just disappear. They just go on to become a part of something else. It's a pretty powerful idea, connecting a fundamental law of chemistry right back to our everyday lives.